Apologies for my Romanian. Unfortunately, I don't speak that language, and you'll see also my accent in French is pretty interesting. So, of course, today we'll talk about hydrogen. I'll start talking about a little bit of solar turbines to tell you who we are. We'll see a little bit of microeconomics, and then we'll deep a little bit in the technical side to look at what solar turbines can do with hydrogen and the impact of hydrogen in the gas turbine. So let's start with solar turbines. If you don't know us already, solar turbines is then the largest manufacturer of industrial gas turbines. Not the largest turbines, but let's say the most numerous gas turbines sold. You see on this slide 6,000 gas turbines sold since the beginning of our story. We are part of Caterpillar since 1981. This is important. But compared to Caterpillar, we are not selling through dealers, we are selling directly. So if you want to buy a gas turbine from us, you need to go through solar turbines sales and services. We are present all over the world, really installed in more than 100 countries. We have 65 sales and services locations. So really you will always find our reps and salespeople around you. So let's see a little bit. Well, you saw on the first presentation what's happening with hydrogen in Romania. We'll cover a little bit that here, but you already had a good understanding before. So what is happening? This slide is a bit busy, but try to represent what is happening in Europe before Ukraine actually being accelerated even more now, at least regarding hydrogen. So what we are currently seeing, so an increase of fossil fuel cost, and we are currently wondering if natural gas will be available in enough quantities and actually at which cost. We have seen cost of CO2 increasing, significant burst late last year, but still high, and will keep on being high due to the market design itself. We have seen for the last 10 years a significant decrease in renewable electricity production costs. And also we have seen digitalization increase and increase of H2 biogas and CS, so carbon capture, storage and utilization development. And what you are seeing with what is happening in the east with Ukraine, lots of the forces are also pushing this effort toward more investment in renewable hydrogen. So this is important for today. When we talk about Romania, you are more, you're best to know, but on the left side, we see Transgaz decided to enter into the Hydrogen Backbone Initiative. What is this Hydrogen Backbone Initiative? That's an association, let's say, of main European gas TSOs. And you see these greenish countries, which are all part of this project backbone. And the idea here is to put in place some plan, try to put some visibility on how, what could be like 100% H2 pipeline network in Europe. And this extract of those two pictures are an extract from a report. If you could click on this link when you have the presentation. This is a report that is showing an acceleration of potential plan to get sooner H2 in Europe, also due to what is happening in the east. And what you can see here, seeing Romania on this side already in 2030, with blue and green H2 potential import. There is a good chance that H2 will be available already by 2030 around this pipeline, and even more on the right-hand side if in 2040. So good for hydrogen at least. Looking at hydrogen, so let's now look at our capabilities and what is the impact of hydrogen into a gas turbine. And we'll look in particular in combustion, but let's see that. So this is a slide that is trying to show what is our experience in hydrogen. So first thing, it's clear on the top, so just so that you do not forget. So we are able to do 100% H2. But also showing that hydrogen is not a new stuff for us. So we have been seeing this, let's say, big hype in the news since, let's say, 2 years, let's say, something like this. But we have been working with hydrogen solar turbines with hydrogen since 1985, almost 40 years. You see on the left-hand side, first experience with a refinery with an off-gas that was 40% hydrogen rich. So already in 1985, this is definitely important. And you can imagine in 40 years, because those units actually have retired only a couple of years ago. So we have gathered a huge experience in material selection, in the operations with hydrogen, with safety, emissions, etc. So huge experience gained there. So going on the right direction, so 1995, first experience with 100% H2, already then. 2003, very important date as well. First DLE, we call it in solar Solonox, that's the brand for DLE. First DLE we've tested with 15% H2 and running since then and still now with 9% H2 continuously. 2005 up to 2018, start of the experience with the steel gases, which in this case coke oven gas, which is 55 to 65% H2, reaching 46 units installed. That's also a very big number. 2021, we reached for all the H2 operations already 2 million operating hours. And one very nice milestone that is in reference that is being installed, that will be a unit that will run up to 83 H2 volume in the gas turbine, the Titan 130 again 15 megawatt machine. So all in all, currently we have 55 units operation in hydrogen fuels, so more than 2 million operating hours, including 5 Titan 130s, which are 15 megawatt electrical DLE units. So looking a little bit in the technical side again, these are all the impact of hydrogen in the gas turbine. It's busy, but I will not go in detail on that. But just, of course, hydrogen is a different molecule than natural gas, and you see impact on the temperature of the flame, on diffusivity, it's very small molecule. Reaction, the energy content by kilo by volume, very different from natural gas. And on left side, you see the impact that has on the gas turbine. So potential flashbacks, emissions, emission stability, operability, component durability, embottlement, safety, starter flame detection. Next slide, we'll talk about only combustion after our first slide on performance, because it's something that needs to be clarified. This is the slide on performance, just to be sure that everybody understands there is no impact or very small impact on the upside on performance with hydrogen, with gas turbines, to be clear. Just to clarify that with some other technologies, there is a strong impact, 40–50%. Derating with gas turbine, there is no derating at all. This is a slide going to 30% H2, but it's the same up to 100%. It's actually a little bit more power, a little bit more efficiency, but it's on the tens of percent impact. Turbine combustion. This is the main piece to understand the difference. This is the main impact. So typically we have two systems of combustions. Apologies for the ones that are more technically savvy. Diffusion flames and premixed flame. That's the gas turbine technology. Use these two technologies. And the idea is to why you change from diffusion to premixed flame is to control the temperature of the flame. You see the small schematics at the bottom of the slide, and the white numbers. So with the premixed flame, you manage to decrease the flame temperature quite significantly. And what is important there is that the NOx that are produced are directly driven or mainly driven by the temperature of the flame. So if you use the DLE, you try to minimize the flame temperature and decrease the NOx. That's the point. Currently, what you can offer on the hydrogen piece is up to 100% H2 will go on the conventional, and on the DLE side we can go up to 20%. This number 20% is evolving quite a lot, so don't be surprised in within this year or next year this number will significantly increase. So let's look again on some differences. So lean premixed flame, so premixed or DLE or Sonox, these are the same names for solar. So you see the fuel and the air is mixing inside the injector. This is a simplified injector here. And the flame is sitting inside the combustion chamber, easily right here. What is happening in the premixed flame? There are some competition between two processes. This competition between the flame speed. So the flame is going toward the fuel injector. And competition between the flame speed and the fuel and air blend velocity. So this is going in this direction. So you see there is competition between the flame speed that is going in this direction. The more the fuel and air speed is, the bigger it is, the further will the flame go out of the fuel injectors. So this is exactly here that the hydrogen takes place here. Okay, small busy slide. On the left-hand side, you see what is important with the design of a fuel injector with hydrogen. Hydrogen has a flame speed, a flame velocity. It is almost 6 to 7 times the one of natural gas. And what does it mean? And you'll see the impact on these two nice video here. Then I was talking about the competition between the two processes. Here, the flame is going faster than the blend velocity, and the flame is entering into the fuel injector. So this is definitely an issue because this is not made to stay in there. So you will have a damage to the fuel injector. This is exactly the point of designing an injector in terms of fuel velocity. Here you see the same kind of impact, but with oscillations of the flame going inside the fuel injector, and you can have damage also due to the vibrations oscillations. On the bottom of this slide, you see the impact of flame temperature, also because hydrogen is another molecule, so with higher diabatic flame temperature. And here you see a difference between pure natural gas and pure hydrogen, quite a significant difference. And as I said before, there is a strong correlation between NOx emissions and flame temperature. So this is a parameter to be taken into account, and this is not, let's say, a real issue for combustion engineers, but you need to design your injector for that. So if your injector was designed for natural gas, you will have an issue with flame velocity, flashbacks, and potentially an issue with emissions. Let's see even better in this slide. This is an experiment. You see the difference between two fuel injectors, the new production and the legacy, so the old production. The old engine, let's say, was 10 years ago in the field. Here you have a picture of the flames with the same conditions, 30% H2 natural gas, pressure, etc. the same. And you see on the top with the new injector where the flame is nicely, you see this yellowish, this bluish cone. The flame is inside the combustor nicely. On the bottom, you see the flame is actually entered into the injectors, and you see the tip of the injector that is going white hot, and there will be significant damage in terms of seconds. So this is what we mean with designing an injector for hydrogen and not for hydrogen. Of course, I said we are able to do 100% H2 unconventional. We are also going toward the development of 100% H2 with DLE, and we are at the moment planning to have the system available for 2029, 2030. This is the target, or what we assume the market will need this kind of product. If it's earlier, we'll have to accelerate this roadmap. Okay, nice. Last point, just to make things, let's say, clearer. We can do 100% of H2 today. You can today buy 100% H2 combustor and the gas turbine package. You can imagine to buy a package today with this capability, install a gas turbine burning natural gas. When its H2 is available to your plant, you can so manage it in your gas turbines. And by 2029, you could upgrade your package that is a new gas turbine that is conventional to a new DLE package that will be available at this stage. On the right hand side, at the bottom, just to a small graph to let people understand that emissions are anyway manageable, even with conventional. We are able, with today's technology, with wet emissions and SCRs, to meet emissions that are typical of a DLE combustor. So this is not an issue on this side. Last slide for my side on the conclusion. So we saw at the very beginning that the current forces are favoring the earlier adoption of H2, at least earlier availability of H2. Transgaz has chosen to be part of the European H2 backbone, so which is likely to accelerate H2 deployment in Romania. As I showed just a few slides ago, solar turbines is available today. Solar turbines, gas turbines are available today with 100% H2 capability. A solar turbine is investing in hydrogen gas turbine technology, particularly DLE, but also other capabilities, to make solar turbine package future-proof. That's it for my side, Gabriel. To you.
Thank you. Thank you very much, Benoit, for the presentation.